Part 2, this is for questions 11 to 20. Question 11, 50 cubic centimeters of 1 molar sulfuric acid is added to 100 cubic centimeters of 1 molar sodium hydroxide in an insulated vessel. Both solutions are at the same temperature of 20 degrees C before mixing. After mixing, the temperature rises and the highest temperature reached is 29 degrees C. So since there is increase in temperature around the surrounding, that means there has been energy loss to the surrounding. Okay, energy has been released to the surrounding. So this is an exothermic reaction. So the enthalpy of a reaction here is going to be a negative. So that's why you're seeing a negative on all the answers you are seeing here. Okay, then they are saying that assume that all the energy released in the reaction goes into raising the temperature of the aqueous reaction mixture. The specific capacity of the mixture is 4.2 joules per centimeter squared per Kelvin. What is the value of the enthalpy of neutralization determined from this experiment? Now, enthalpy of neutralization, will look at 1 mole of water formed when an acid reacts with a base. Okay, now from here we have sulfuric acid aqueous, then plus sodium hydroxide also aqueous, then this one will give us sodium sulfate, then plus water. Okay, we form water here, but balancing this equation, I'll put a 2 here. Now hydrogen is 2 and also 2, that one becomes a 4. That means I will put a 2 here to also make this one a 4. Oxygen is 2 plus the 4, that is a 6. 2 plus the 4, that is a 6. And then of course here sodium is 2, then sodium is 2, sulfur is 1, and then 1 also the other side. Now let us look at the moles of the reaction. We see which one is the limiting reagent. Okay, now when you look at this one for sulfuric acid, the moles will be 50, then it has to be out of 1,000, then times 1. This one will give us 0.05. Okay, 0.05 moles. Now this one here for sodium hydroxide, we have 100 times that. So it is 100, then times 1 out of 1,000. This one is what? 0.1. Okay, but now when you look at this stoichiometry here, by looking at just what we are having here, the moles of sulfuric acid are smaller, okay, than the moles of sodium hydroxide. Now, so we shall take the moles of sulfuric acid here. This one becomes the limiting what? Reagent. But now for 1 mole of sulfuric acid here, we need 2 moles of sodium hydroxide. So that means if we are taking 0.05 moles, okay, then here we shall take 2, okay, 2 then times the 0.05, okay, and actually it will give us 0.1, which is exactly what we are having here. So that means they all react completely. Okay, now we know that energy change is going to be equal to mc, sometimes we put theta, or change in temperature. So the mass for aqueous solutions, if you have an aqueous solution here and also this one here, all of them are aqueous, then you add them together, then you cause the reaction. This one is going to be the mass here. Remember, we assume that 1 cubic centimeter, okay, is equivalent to 1 gram. So we shall have 50, then plus 100, which will become 100 and what? And 50, okay? 150 grams, then times the specific heat capacity of water, because all of these ones were dissolved in water, okay, to form the solution. So it is 4.2, then times the temperature change is going to be a 9, from 20 to 29, okay? Now when we multiply everything here, what do we get? 150 times 4.2 times 9. So this is 5670, 5670 joules. Okay, now this means these moles here which reacted, these moles here are the ones that released what? That released this 5670 joules. Okay, so we shall say 0.05 moles. Okay, released 5670 joules. Now how about 1 mole? Okay, how about 1 mole of sulfuric acid? But you can see that 1 mole of sulfuric acid releases what? 2 moles of water. Okay, and yet when we are looking at enthalpy of neutralization, we are looking at 1 mole of water being formed. So you have hydrogen ions here, then plus the OH ions here. Okay, then to give us water as a liquid, 1 mole. So the enthalpy of reaction here will be the enthalpy of neutralization. You see that? That is the one which will give us that. But we see that 1 mole of sulfuric acid here releases 2 moles of what? Water. That means for when we are getting the enthalpy of neutralization, because this one releases 2 moles, then we shall divide it by 2. You get that? So 1 mole of sulfuric acid would release we can say 110 times the 5670, then we divide by 0.05. What do you get here? So what we are having here, we divide it by 0.05. This one is 113.400 joules. Okay, but this one here is for 2 moles. 2 moles of what? Water, but we need for 1 mole of water. So for 1 mole of water, okay, energy released will be equal to a half of what we are having here. Okay, now when we get a half of this, what does it give us? So the answer I'm having here, divide it by 2, we get 56700 joules in kilojoules. Because this one will be per mole. Okay, because we are looking for 1 mole. You see that? And then this one is going to, you divide by 1000, so it will be 56.7 kilojoules per mole. So here I used this language, energy released. So here I don't need to put on a negative, okay? But when I'm just writing that figure without saying energy released, then it has a what? A minus. So my answer then becomes what? A B. Question 12. Barium dithionate is soluble in water. Then the dithionate ions slowly decompose in acidic solution to give us sulfur dioxide and the sulfate ion. They are saying 3.513 grams of this dithionate, barium dithionate, is dissolved in water in 100 cubic centimeter volumetric flask, and the solution made up to the mark with HCl. At time x minutes, a white precipitate of mass 0.661 grams is present in the flask. What is the concentration of barium dithionate in the volumetric flask at time x minutes? Now, since this one dissolves, okay, in solution, that means it is going to separate into this ion here, okay, and then barium barium ions. So you have here barium dithionate, okay, this one dissolves in water to give you barium ions, okay, and then we also have what? This thionate ion, 2 minus, then plus the water, okay. Now this one breaks down into the sulfur dioxide and what? The sodium, the sulfate. And now in this solution, since we have barium ions, then plus this sulfate ions, this one is the one that is going to give us the white precipitate, okay? That solid here, whose mass is this one here. So that means we shall begin by finding the number of moles which are in this mass of barium sulfate. Then after getting those number of moles, they will be equal to the number of moles of the sulfate ions here, or barium ions. Okay, so since they are the same number of moles of the barium ions here, because remember what is reacting here is what is produced here. Okay, so those number of moles will again be equal to the number of moles of this barium thionate. You see that? So now let's begin. I'll begin by finding moles of barium sulfate. Okay, this one will be equal to 0.661 out of, we need the MR of this one. So what is the AR of barium? Because that one of sulfur is 32.1, then plus oxygen, this one is 16. So we need the one of barium. When we come to the periodic table, for barium it is 137.3. 137.3. So what does this one give us? 0.661. Then we divide by 137.3, then plus 32.1 plus 4 into 16. And this one will give us 2.832. 2.832 times 10 to power negative 3 moles. These ones here are going to be the same moles for the barium ions, or this, because the reaction mole ratio is 1 to 1. Are we there? It is 1 to 1. The moles we have gotten here are for this solid. So since the reaction mole ratio is 1 to 1, they are the same moles for the sulfate or barium ions. Okay, now those are the ones that have been produced here, and those number of moles are going to be equal to the moles of this barium dithionate. Okay, so I will say that moles of barium dithionate here, this one here, that reacted, okay, or that dissolved in the water, that dissolved in water, it is this same figure here. Okay, so let me just put it there. After that, but we have the original number of moles, original number of moles of barium dithionate. From here, so this one is going to be 3.513, then divide by barium, we saw it is 137.3. Sulfur is 32.1, then oxygen 16, then water, this is 2 plus the 16, the mass of water is going to be 18. Okay, so 18 times 2 times the 18. Okay, so this one is going to give us what? 3.513. Then we divide by 137.3 plus 2 times 32.1 plus 6 times 16 plus 2 times 18. Okay, then this one will give us 0.010533. Okay, now these are the moles which were there, which are in this. Okay, But the ones that dissolved, okay, that gave us this one here, the mass here, when this time had elapsed, okay, when this time had elapsed, they were these ones here. Okay, so from the original we are having this, but these are the ones that gave us the what? The white precipitate. And they are asking us to find the concentration of this barium diethionate in the volumetric flask at this time. So what is remaining? We can say remaining moles of barium diethionate. This one is going to be 0.0105337. Then we subtract the 2.832 times 10 to the power negative 3. Then after that, what we get here, these are the moles that are contained in the 100 cubic centimeters, okay? What about in a liter? Because here you can see moles per liter. So what I get here, I'll just multiply it by 10. Then the concentration shall be equal to 10 times what I have here, times everything here. Why am I multiplying it by 10? Because 100 cubic centimeter goes into 1,000 10 times. In other words, I'm saying 100 cubic centimeters contain this number of moles, okay? Then how about 1,000 cubic centimeters? So then 1,000 cubic centimeters will contain 1,000, then times those number of moles, then divide by 100. So 100 goes here 10 times. So that's why I'm multiplying by 10 here. You see that? Okay. Now when we put this in the calculator, what do we get? That will be our answer. So this one here, I will say minus 2.832, then times 10 to the power of negative 3, okay? So times 10 to the power negative 3. What I get, then I multiply by what? By 10. So this one will give us 0.077 moles per liter. And our answer from here is going to be a C. Question 13. The diagram shows two containers of methane connected by a closed tap. Each container has a volume of 1 meter cubed. So these are the ones here. We are seeing 16 grams of methane. What will be the moles here? So moles of methane will be 16, then divide by what is the MR of methane? This is 12 plus 4, that will also be 16. So this is 1 mole, okay? Then when we come to this one here, moles of methane in 96 grams will be 96 out of the 16. And this one will give us 16 moles, right? Then they are saying that the tap is opened. So when you open the tap, that means these ones are going to mix, okay? So altogether we are having 7 moles, 1 mole this way, and then the 6 moles this way. So altogether we're having what? 7 moles. So these 7 moles are going to mix themselves in here, and the total volume is going to be this one here times 2. Are we there? It is going to be 2 meters what? Cubed, because here we have 1 meter cubed, and also here we have 1 meter cubed. So the gas molecules are going to move and then occupy that what? Whole volume. So the tap is open, the temperature of the system is changed to 800 K. The system reaches constant pressure. Now when you increase the temperature, that means these gas molecules are going to get energy, and then they are going to start moving faster. Then the collisions are going to be much more often onto the walls of the containers. So in that case, pressure is going to do what? Pressure is going to maybe increase, okay? But we need to find the pressure that is going to result out of this. And that is exactly what they want us to find. The system reaches constant pressure. What is the pressure of methane within the system? We know that PV is equal to nRT. Okay, we want to get pressure, so nRT, then out of V. Now, in here, pressure is in pascals or newtons per meter squared. Okay, volume has to be for an ideal gas, volume has to be in meters. Okay, in meters what cubed, since here we are having meters squared as the area, because remember pressure is force over area. Okay, force over area. So we have to find a connection in those SI units. And then temperature has to be in what? In kelvins. Now our pressure is going to be the number of moles. Remember we have 6 here plus 1. That is what? 7. Then plus the molar gas constant is 8.31 times the temperature has been given to us as 800 K. Then we shall divide by the volume is now 2. Okay, 1 meter cubed here and 1 meter cubed here, so it is 2 meters cubed. Okay, 2 meters cubed. Then what do we get here? 7 times 8.31 times 800. Then we divide by 2. This one is 23268. 23268. These are pascals, but when we look at our answers here, we are having kilopascals. So that is the same as 2.3. No. You divide this by 1,000, so it will be 23.268 kilopascals. And our answer therefore becomes A. Question 14. Which statement about a 3p orbital is correct? A 3p orbital. It can hold a maximum of 6 electrons. No. A p orbital, actually, the 3p as a subshell, it has 3 orbitals. Okay, p orbital has, a 3p subshell. Now that is the confusion. So you might think, and indeed it is true, this subshell here is having, it must have a maximum of 6 what? Electrons, but they are talking about orbital. So they mean this one here, this one here, this one here. So this is the orbital. This one here, and that one there. You see? So that means this one here is not correct. So A is off. Each of them holds a maximum of 2 electrons. Then it has the highest energy of the orbitals with principal quantum number 3. Even this one is wrong. Why? Because we have 3D. Okay, on the third principal quantum number we have 3s2, 3p something, maybe 6. Then there is also 3d something. So it is not the one with the highest. You see that? And then next, it is at a higher energy level than the 3s orbital. That is true, because the 3s might be here, then the 3p is there, and then but has the same shape. No, S has this spherical shape, and then the P, its shape is lobular. It is like that. So this one is correct, but this one is wrong. You see that? So that simply implies that our answer here is also wrong here, the C. So that means the only option left is D. It is occupied by 1 electron in an isolated phosphorus atom. So you get phosphorus here. Its electron configuration is 1s2, 2s2, 2p6, those are 10, then 3s2, then 3p3. Okay, they said it is occupied by 1 electron. So when you look at the p orbital here, the 3p orbitals here, each of them has 1 electron. You see? So the orbital is occupied by 1 electron. So that's why our answer is what? Is D. Question 15. In which pair do both species have the same shape and have the same number of covalent bonds? So here I'm seeing methane and ammonium ion. So methane is CH4. Ammonium ion is this one here. Now methane has a tetrahedral structure. We have that. And even this one, ammonium ion, there is a coordinate bond here, which is given to the hydrogen. So first of all, we have ammonia, which has a lone pair of electrons here, and then you have a hydrogen ion. Then this one donates the 2 electrons to this ammonium ion. You see that? And then there is a coordinate bond that is formed here. Remember, for a coordinate bond, one species donates, or one atom donates the what? The electrons in that covalent bond that is being formed. So this one will have the positive charge because it appears to have lost the what? The electrons. You see that? And then we shall have that. Now, first of all, ammonia is having the trigonal pyramidal shape. Okay, there is a lone pair of electrons there, and then we have what we call in fact, when you look at this, there is also ammonia here. So suppose I bring this one down here, it will make much more sense. There is ammonia. Now, when using valence shell electron pair repulsion theory, we are going to have the lone pair bond pair repulsion. This lone pair bond pair repulsion is stronger than bond pair repulsion. Okay, so right from here, this one which is tetrahedral, this is 109.5. Even this one here, it is going to be 109.5. It is the same for these. Okay. Then what are we having here? These are all hydrogens. Now, for this one here, because the lone pair bond pair repulsion is stronger than the bond pair repulsion, okay, this one is going to press these bonds here much further. That means the bond in the angle in between them is going to be less than the 109.5. That's why it is going to become like 107 degrees. You see that? Then these ones, by the way, have a tetrahedral shape, both of them. Okay, this one and this. Then they say they have the same number of covalent bonds. Yes, this is 1, 2, 3, 4. This is 1, 2, 3. Even this one here, it is a coordinate bond, but it is a covalent bond, because covalent bonding is sharing of electrons, okay, between the two atoms. So even these two have the same covalent bond. So it looks like the answer is actually A. But let us look at these other ones here. Carbon dioxide and nitrogen. Carbon dioxide is this one here. Its shape is going to be linear. So it is like that. And we are seeing four forward covalent bonds. So here there are 2, and then here there are 2. Then nitrogen, which is a diatomic molecule, we are seeing a strong triple bond. Okay, all of them are linear, but the number of covalent bonds shared here, they are 6, because it's a triple bond. Each bond has 2 electrons. Okay, so those are 6, and yet here we are seeing 4. So this one has to be off. Boron trifluoride. This is boron. Then you have fluorine. This one, the angle is 120. Okay, the fact that these two do not have the same shape, so already this one is off. What about water and oxygen? So water, you have oxygen here, then hydrogen and hydrogen here. Of course, we have the 2 lone pairs here. The lone pair repulsion is much more stronger than bond pair lone pair repulsion, and also in turn stronger than bond pair. So by removing another bond pair here, and then we replace it with a lone pair, so there is going to be a strong repulsion here. Okay, which in turn is going to uh, press these ones here, and then you find that the angle is going to be smaller than 107. You see that? So the bond in between here is smaller than 107 because of this bigger repulsion between the lone pairs. Okay, so that means here we shall have an angle like 105 or 104.5. Sometimes you find when they put 104 then to 105, but the average is 104.5. Okay, so that is that. Of course, oxygen here is linear. Okay, they don't have the same shape. This one is V-shaped and this one is not. So even this one is off. So our answer is what? Is A. Question 16. A reaction involving ammonium ions is shown here. And they are saying four statements about this reaction listed. The ammonium ions are reduced. If ammonium ions are reduced, then let us first see what is reduction. Reduction is going to be addition of hydrogen or removal of oxygen. But we see that ammonium ions here have lost the hydrogen. So when you lose hydrogen, then you are oxidized. You are not reduced. You see that? But let's look at the oxidation states here. The one for hydrogen is +1. And then for ammonia, if you have N, then +1, then is equal to +1. But by the way, each of the hydrogens, how many do we have? We have 4. Then times 1, then is equal to a +1 that is here. Okay. Then you take the 4 here, 1 minus 4, you get a -3, not so? So this one is -3. Let's look at the N here. So we have N, then +3 times 1, then you get a 0 because this one is not charged. Again, N is going to be equal to -3 from here. Hydrogen is 1. So there is no change even in the what? In the oxidation states. So that means we are not talking about oxidation and reduction here. Of course, for oxygen, it is -2. For hydrogen, it's +1. Even here, it is +1. Then for oxygen, it is -2. Okay. Now, that means this one is off. Okay. In reverse reaction, it is off because we are not seeing the change in the what? In the oxidation state of ammonia or of nitrogen in ammonium ions and also ammonia. Then statement 2, they are saying in the reverse reaction, ammonia acts as a Bronsted-Lowry base. Now, first of all, before I even do anything else, wherever there is 1, I have to cancel it. So there is a 1 here. There is also a 1 here. So that means my answer has to be on C and D. Now let's go to statement 2. In the reverse reaction, ammonia acts as a Bronsted-Lowry base. So reverse, we are looking at this. A Bronsted-Lowry base is the one that accepts a proton. Okay, so ammonia here, when it accepts a proton, then you will have ammonium ions. Okay, it is like this. It has a lone pair of electrons, so it donates them to the proton. This one is called a proton because hydrogen has 1 electron in the what? In the outermost. Now it has lost it. There is 1 proton in the nucleus which is positively charged. Now if it has lost this electron, it is that only proton that is moving now. So that's why hydrogen ions, we call them protons. You see that? Now you will get the ammonium ions. Just like in the previous number, you will attain a tetrahedral structure from the trigonal pyramid. Now, so this one is actually correct. So where there is a 2, it is correct. You see? Now there is no 2 in here, and yet it is correct. So that means our answer actually has to be a C. But let's continue and we see. When you go to 3, they are saying the ammonium ion and the ammonium molecule have the same bond angle. Right from the previous number, ammonium ion, we are seeing that it has the bond angle here is what? 109.5 for the tetrahedral structure. And then ammonia, the angle we have seen here. What is the angle? The angle is 107. You see that? 107. So it is not the same. So 3 is off. And here there is a 3. So that's why this one is also off. But then 4, they are saying this reaction is not a redox reaction. Indeed, it is not a redox reaction because we are not seeing changes in oxidation what? States. You can see for ammonia, it is -3, -3. I mean for nitrogen. Then hydrogen, we are seeing +1 everywhere. Oxygen does not also change. So it is true, indeed, that this reaction is not a redox reaction. So that's why our answer is C. Question 17. Which reduction process occurs on the surface of a catalytic converter? A catalytic converter. So in the catalytic converter, we have nitrogen monoxide here, which reacts with carbon monoxide. Okay. This one, which would have been so toxic. And then we get carbon dioxide, then plus what? Nitrogen as a gas. Now we're trying to balance this. Since nitrogen is 2 here, I can put a 2 here. Okay. Then oxygen becomes 3, but if I put a 2 here, oxygen will be 4. That means when I put a 2 here, I'll get oxygen 4 here, as it is here, but also carbon is now 2, and it is also 2 here. So that is the balanced one. Now, if these nitrogen oxides are released into the atmosphere, they will go into the atmosphere, then they react with the sulfur dioxide, because remember, sulfur is an impurity in these fossil fuels, okay, that are burnt. And then you will get the nitrogen dioxide, let's say in the air, then reacting with sulfur dioxide to give you sulfur trioxide. You see that? Then plus what? Nitrogen monoxide. And then the nitrogen monoxide there, because there is available oxygen in the atmosphere, it will react with more oxygen, okay, and then to give you a nitrogen dioxide. So the process continues. So that's why this one is called catalytic oxidation of sulfur dioxide, because in doing so, you are seeing that this one, which appears to be consumed here, is regenerated here. That's why nitrogen dioxide acts as a catalyst. So we call it catalytic oxidation of sulfur dioxide. You see that? And then at the end of it all, then this one here, the sulfur trioxide produced, will react with the moisture in atmosphere, then to give you the sulfuric acid, which we call acid rain. You see that? So like that. Now, when we come to what we are having here in the catalytic converter, this is the reaction that we are having. So you can see that the nitrogen monoxide here is reduced because now it loses this oxygen, okay, and then we get the nitrogen here. Then the carbon monoxide is oxidized to carbon dioxide. You see that? So we are seeing here a reduction process. Then we are seeing here an oxidation process. So they are saying in the options here, reduction of carbon dioxide and nitrogen oxides. This one is wrong. We have seen that this one is oxidized, I mean reduced, and then this one is oxidized. Then reduction of carbon dioxide only. Carbon dioxide is actually oxidized, so that is wrong. Then reduction of nitrogen oxides only. Yes, there is reduction of these nitrogen oxides, so this one is correct. But then the reduction of carbon monoxide is what? Oxidized. You see that? So our answer is C. Question 18. 3 statements about the halogens chlorine, bromine, and iodine and their compounds are listed. Then 1, we are having the halogen with the highest boiling point. With the highest boiling point is going to be what? Iodine. Okay? Iodine. Why? Because going down the group, the number of electrons increases. And when the number of electrons increases for these nonmetals, we are going to see that the strength of the ID forces, or the intermolecular forces of attraction, they are going to increase. And if the strength of intermolecular forces increases, then that means that it is going to take some good energy to break those bonds. Okay, so the number of electrons increase down the group, the ID forces increase in strength. That is why iodine is able to stay as a solid under room temperature, then bromine as a liquid, and then chlorine as a gas. You see that? So they are saying the halogen with the highest boiling point, which is iodine, has atoms which form the strongest bond to hydrogen. Now, we have hydrogen iodide. This one is wrong. Okay? This one here is wrong. Why? Because iodine is very big. Okay? So because iodine is very big, when this hydrogen here shares electrons with the iodine that we are having here, because of this distance between these bonding electrons and the nucleus of iodine, okay, we are going to have a weaker attraction of these electrons. So the bond is going to be longer. The longer the bond, the weaker the bond. Okay? Okay, so that means you cannot say that which form the strongest bond. So this one is off. So wherever there is one, I will just cross it out. That means my answer has to be on C or what? Or D. Okay? Then we go to statement 2. The halogen with the strongest ID-ID attractions. Which one? ID-ID attractions. That one is, again, iodine. Okay? Forms the most thermally stable hydrogen halide. So when you look at the hydrogen halide here, going down the group, the bond energies decrease. Okay, this one is easily converted into its elements and you get hydrogen, then iodine. Because of what I talked about here, it's a long bond and it is weaker, so it can easily break down. You see that? So forms the most thermally stable. So even this one is wrong. So wherever there is 2, I'll cross it out. So I'm remaining with only 3 here, which is D. The most volatile element most rapidly oxidizes hydrogen. That is the chlorine, the most volatile. So volatility is the ease to vaporize. Okay. So now chlorine here, when it reacts with hydrogen, then you can get the HCl. Okay. The oxidation state of chlorine here is 0. Here it is -1. For hydrogen, it's a +1, then 0. Now you can see that from 0 to -1, that is reduction, not so? But then from 0 to +1, that is oxidation. So hydrogen is oxidized. So they are saying the most volatile element most rapidly oxidizes the what? The hydrogen. You see that? So that's why our answer is what? Is a D there. Question 19. Which reagent or reagents and conditions will oxidize chlorine into a compound containing chlorine in the +5 oxidation state? Then we look at whatever is given here, and there is cold dilute and then hot concentrated. So these are the ones I'm going to concentrate on. We have sodium hydroxide reacting with chlorine. Under cold dilute sodium what? Hydroxide, you are going to get sodium chloride, then sodium chlorate 1, okay? And then we shall also have water. Then when it is reacting with hot concentrated, this one is hot concentrated sodium hydroxide, we are going to get again sodium chloride, then plus sodium perchlorate, okay, perchlorate like that, and then water. So to balance these ones here, these are 2 sodiums, so suppose I put a 2 here, then hydrogen becomes 2, even hydrogen is 2 here, oxygen is now 2, oxygen is also 2, then chlorine is 1 and 1, those are 2, even here it is 2, so that one is balanced. And then here we are having oxygen is 3, and then this one is 1. Now, suppose I put a 3 here, this one will make oxygen 6. So when it makes oxygen 6, I will put a 6 here, okay, for oxygen to be 6. And then sodium here is also 6. That means I can put a 5 here to have 5 plus 1. Okay. And then let's go to chlorine. Chlorine is what? 5 plus 1. That is 6. So I'll put a 3 here. So that is what we are going to have. Now, what is the oxidation state of sodium? Is plus 1. Even here, plus 1. Oxygen is minus 2, plus 1 for hydrogen, then plus 1 for hydrogen. Here, chlorine is 0, 0. Then again here, plus 1. Then this will be minus 1. This is plus 1, then minus 1. Actually, these are disproportionation reactions, okay? Because we are seeing chlorine here. It is changing. This is a reduction. So what happens in here? This is plus 1. How about chlorine in here? Remember, this is minus 2. So we have 1 plus n, then minus 2 is equal to 0. So our n is going to be, this will be a minus 1. 1 minus 2 is a minus 1. So when it crosses the equal signs, it's a plus 1. So even here, this one will be a plus 1. So you can see that this is reduction and this is oxidation because of the increase in oxidation state. So that is what we call a disproportionation reaction. The same species undergoes reduction and what? Oxidation. Then when we come to this one, it is plus 1, and then this is minus 2. So we are going to have 1. You have 1, then plus n, then plus. We have 3 oxygen atoms. Each of them has oxidation state negative 2. Then we equate to 0 because it is not charged. And then we have minus 6 plus 1. That's a minus 5. So when it crosses the equal signs, then we get a plus 5. So this is a plus 5. You see, from 0 to plus 5, that is oxidation. Then from 0 to minus 1, that is a reduction. You see that? Of course, this one remains as a plus 1, and then a minus 2, plus 1, and then a minus 2. And they are looking for, they are saying that the one in which chlorine has oxidation state what? Plus 5, and we see it here. So that means our answer is D. I will not even look at anything else here. Question 20. Which diagram shows the electronegativity of elements sodium, magnesium, aluminium, and silicon plotted against their first ionization energies? Now, when you look at first ionization energies of these period 3 elements, it has to be increasing, okay? It has to be increasing generally, because you are adding electrons to the same shell, okay, as you go around, across the period. You see, you're adding electrons to the same shell, so there is constant shielding. And as you're adding the electron to the outermost shell, there is also a proton added to the nucleus, so the nuclear charge increases, and also the nuclear attraction for the outermost electron increases. Okay, so for that case, then we are going to find that to remove an electron as you go across the period, it becomes a little bit harder. So because of the stronger nuclear attraction for the valence shell electrons, so that's why ionization energies increase across the period. Okay, so we are supposed to look at this and this, where ionization energy is increasing as you go down the group. Of course, we have those small anomalies in there based on the shells increasing, those subshells, because you are moving, like, let's say from 3s2, 3s2, then there is 3p, something like that. Now, when these ones are decreasing, that first ionization energy decreases across the period as you continue to this silicon. So these two have to be wrong. Generally, the first ionization energy increases. So let's look at A and B. Now we go to electronegativity. For electronegativity, it becomes much more evident in the nonmetals, because for them they react by gaining an electron. And electronegativity is that energy change when 1 mole of electrons is added to a gaseous atom. You see that? So metals actually react by losing electrons. So that means they are less electronegative. You see that? Because for them, they lose them. The ones that are much more electronegative are the ones that gain the electrons. So that means electronegativity, okay, has to be increasing towards the what? The nonmetals. Now look at these ones here. Look at sodium. Sodium has 1 electron in the outermost. So let me look at 3s1. Okay. It can easily lose this electron to become a sodium ion. So its electronegativity is going to be so low. So this one is okay and this one is okay, very low. And even the first ionization energy is too low because this is a new shell when you look at the 1s2, 2s2, 2p6 here. So it becomes very easy to remove that electron because of the longer distance from the nucleus. Okay. Then I can also look at now which one is next in line, magnesium. So let me just consider the electrons in the outermost. So magnesium has 3s2. Okay. Now this one has a higher first ionization energy. Remember, the electrons are added to the same shell, but now this one has a stronger nuclear charge and nuclear attraction. So we expect its ionization energy to be higher than that of sodium. And we can see that it is on the right of sodium. And also here it is on the right of sodium. Okay, this way. So both can be okay. But then let's go to aluminium. Aluminium here has gotten 3s2, then 3p1. Okay, and the s orbital is here, then the p is there. So it's like we have added on one shell here. So that means in here there is nuclear, the nuclear attraction for this electron is going to be a bit weaker because of the addition of a shell. In other words, there is increased shielding. It's a slight change because these two are relatively similar in energy. P is just slightly above the S. Okay. Now, what we are going to have, because of the slight increase in the screening, okay, we are going then to have the ionization energy of aluminium being lower than that of magnesium. You see that? Now, here, the ionization energy of aluminium is above that of magnesium, but here, the ionization energy of aluminium is lower than that of what? Magnesium. And it looks like this one is correct for us because of the increased shielding. Then it becomes very easy to remove this electron from here. So that means our answer has to be a B here.